talk today will be about decision forest, celebrating 20 years since these methods were first introduced to the machine learning community. And during this talk, I'm going to give some insight that I have regarding this kind of methods. I would like to begin with a teaser. It's a paper that was published in JMLR, Journal of Machine Learning Research, one of the most important one in our field, about a year ago, where a team of researchers empirically compared, as you can see here, 179 different classification algorithms over 121 data sets. And they have concluded that random forest, which is one of the most famous or popular decision forest algorithms, reached as top one among all the algorithms that were compared in that experiment. And so practically what we can say is that if you have a new classification task, random forest can be a very good default algorithms to use. Probably you will get good results from that. By the way, I would like to mention that when they use the random forest, they try to build the forest with 500 trees, okay, which is a relatively high number of trees. So the idea, of course, of random forest is to build an ensemble of trees. Each one of the trees can give a prediction to the unseen instance. For instance, in our example, this is a classification task, so each one of the trees provide a classification. And then we have some sort of mechanism that combine all the prediction, or in this case, all the classification into a final one. Specifically, in this example, we are using the majority voting, which is the default way to combine all the results. We have 7 trees, 5 of them have gave the classification of 1 and 2 of them classification of 2, then the final class will be, in this case, of course, 1. The idea of voting actually goes back at least 2 centuries ago with what is known as the jury theorem, which is a very important theorem in social choice. And the idea is that you have a jury with n voters. Each one of them has a probability p to make the right decision. And by mu, we can denote the probability of the entire jury reaching to the correct decision. So in this case, we can formulate mu as a binomial distribution as a function of both n and p. But the more important thing in this theorem is that if p is greater than 0.5, then mu is going to be greater than p. And if n goes to infinity, mu will reach to almost 1. And this is what you can see in this graph at the right side of the slide. Another example is, of course, the wisdom of the crowd. This was done about a century ago by Galton that promoted statistics. He was visiting a fair, and in that fair there was an ox that the participants were asked to estimate the weight of this ox. And while all the participants didn't give a very accurate estimation, still taking the weight, the average of all the estimation gave a very good estimate to the right ox weight. As you can see here, it was only 1 pound away from the actual weight. A few years ago, I think it was 2 or 3 years ago, an Israeli called Lior Rokach replicated this experiment in a TED talk. I think it was in 2012, if I remember correctly. And you actually can see it in YouTube. So in order to the crowd to be wise, there are several criteria that we must meet. One of them is, of course, the diversity of opinion. If all the members will have the same prediction, there is no meaning to do a combination of the results. They should be independent, and this is one of the greatest problems in all the theorem, like the jury theorem. It's very hard to create models that are totally independent. They should be decentralized, meaning that they can learn from local knowledge. And of course, we need some sort of aggregation function that can combine all the results into a final one. Some researchers say that there is a trade-off between two components. One of them is the diversity. We, of course, would like that the individual trees will be diverse on the one hand. And on the other hand, we would like them to be accurate as much as possible, as you can see in the x-axis. But I must say that my conclusion is the following. Ideally, all trees should be accurate, meaning they will provide the correct classification for all instances. But if they are not, we simply should ask them to be wrong on different cases. Okay, so the diversity is only about the cases that they are misclassified instances. So practically, if I have a decision forest of 100 trees, all of them can be 99% correct, but still can be diverse in the way they are misclassified the last 1%. I just want to recall how we usually build decision tree. Usually it is done in a top-down manner, in a greedy top-down manner. In each iteration, we test different kind of features, and based on their performance, like information gain, splitting criteria, or the Gini index, we decide how to split the input space into several subspaces. Usually, this is done in parallel to the principal axis that you can see here. And sometimes, when we run the algorithms, the tree can become very complicated with as you can see here in the left side, with the many rectangles in the graph. So while decision tree has a lot of advantage, they do have some disadvantages, and the decision forest try to overcome these disadvantages. First of all, because it is a greedy algorithm, it sometimes goes into a local minimum. Sometimes decision tree also has a problem of insufficient data. This happens because the decision tree, the size of the data that is available for the algorithms is decreased exponentially as we go down in the tree. So if the data that we have is limited, the decision tree algorithms can run into a problem. And as we also seen in the previous slide, sometimes the decision tree has problem because it has limited representation. It can split usually the space only in parallel to the principal axis. And sometimes, of course, the problem can be cannot be represented as rectangles in the graph, in the space. So if we are trying to combine several decision trees, usually the combination can provide us the building a model that is much more complicated than the individual members. And this is why usually it works, ensemble learning, specifically in decision trees. Another way to explain it is with what is known as the bias-variance decomposition, which is the bias is the tendency of the algorithms to learn the wrong thing over and over, basically because it has limited hypothesis space. On the other hand, the variance component is the tendency of the algorithms to learn things irrespectively due to the real signal because of the randomness that we have in the training set on hand. And usually, if you can see here in the graph, if the decision tree is has a lot of, sorry, let me try to, I don't know if you can see it here. If the decision tree contains a lot of nodes, it usually have a low bias, but high variance. On the other hand, if the decision tree has is relatively small, then we have high bias and low variance. And what we usually do with the decision forest is trying to reduce at least one of the components. If we are looking at the left side, the iterative methods that include the adaptive boosting or gradient boosted tree, they are trying to reduce both the bias and the variance components. But the main disadvantage in this kind of algorithms is that they are very hard to distribute in Hadoop cluster and things like that. Although, as you can see here, there were several attempts in the literature to distribute them in using MapReduce framework. On the right side, you can see the iterative methods, which include methods like random forest and boosting and bagging and so on, which are tries to reduce only the variance error, not including the bias error, but they have the advantage that they can be very easily distributed, for instance, in Hadoop clusters. So I will talk about two main algorithms that I mentioned. The random forest is a very simple one. It's simply a bootstrap random sample with replacement. And then it injects randomness into the algorithms by, instead of going over all the features in the data set, by going over only a random subset of the features. And it's also skip the phase of pruning, which we usually do in individual decision tree learning. Of course, it still cannot solve the problem in case that you see here. In this case, if we do the split in rectangles, which are in parallel to the principal axis, you can see that you need a lot of rectangles, about, I think, about 40 here, instead of only 5 if we could do the split in other way. So one practical approach that can be used in this case is known as rotation forest, that trying to improve the performance of random forest. And the idea here is to first run PCA on the data, and then, and only then, create a decision trees. And many times it can really improve the performance of our forest. 5 years ago, we also saw that we showed that by using random projection, actually you can reach the same performance of a rotation forest, but without the need to do a PCA, which is a relatively complicated algorithms, especially if we have a big data in our hand. The other most popular algorithms is adaptive boosting, or AdaBoost, which is doing the following idea. It's using the following idea. It begins by training a decision tree using the sample as is. And then in the next iteration, what it's doing is looking at the misclassification that was done in the previous iteration. And based on that, it increased the weight that it gives to misclassified instances, and train the model again, the tree again, and so on. And also, instead of simply using majority voting, what it's doing, it's using a weighted voting among the decision trees based on their performance on the training set. So for instance, if you are looking at the tree, the last tree here, because it didn't misclassify any of the instances, it has the highest weight. Oops, sorry. And another thing that is interesting here is the fact that when they invented the algorithms, they've shown that even if the error in the training set reach a level of 0, the test error sometimes continue to decrease by adding additional trees to the forest. And usually we need several hundred of trees in order to provide good predictive performance. This leads us to the next slide, which is what we are doing if the random forest or the decision forest contains too many trees in the ensemble. And of course, it has some drawbacks that needed to be addressed. First of all, it takes a lot of storage. Sometimes, of course, it also reduces comprehensibility. It's prolonged the prediction time, and even, and we have shown that, reduce the predictive performance sometimes. So one way to do it is to remove several trees in the forest and there are several ways to do that. One of them that I published a few years ago is using a very simple formula which measures the merit of a subset of the trees. In the numerator, what we have here is the kappa statistics among the trees and the target attribute, while in the denominator, what we have is the kappa statistics among the trees. So if a subset contains trees that are accurate but are diverse, then the merit of this subset will be higher. And by using a very simple best first search strategy, we have shown that we can reduce the size of the forest to almost 3% of its original size, which makes it much more practical in a real-time application. And still, we even improved the accuracy in this case, about 2% better than the original random forest. Another way to do it is to select the trees dynamically based on the instance that we have in hand. Actually, it is related to things that are being done in multi-agent. This is finding the necessary winner. In this case, I'm going back to the example that I gave in the second slide. We have 7 trees, and we need to give the majority voting for this ensemble. Now, my question is, do we really need all classifiers in this case to give the prediction that the class is 1? Actually, we can use only the first 5, right? And after having only 4, 1, we know that 1 is going to be the majority in any case, right? And if we also can use some, we can agree with some probabilistic results, we can actually even use less than that and still have usually good results. Another thing that we did is trying to reduce the entire forest into a single tree. And this is with the following trick. Instead of building the decision tree based on the original data set, what we did, we trained a forest. And specifically, we used the random forest to train the forest. And then we use the forest to create as many as we want, instances as we want, using simulation. Then, based on the fact that we now have a very large data set, we could build a tree that simulates the results of the entire forest. Of course, it doesn't reach to the same accuracy level, but much higher than the original tree that was trained using only the original training set. So this is a nice trick to create a single tree with high accuracy. We use that in when we are working today in ensemble learning. We are working in a different kind of setting, as you can see here. And we are also dealing with the other tasks beyond the classification task. Of course, it includes the regression trees, survival trees, and so on. And that's it. This is 2 quotes that I found in the internet, one of them of Lior Rokach that they did the ox experiment. And the most important message is that we can reduce the size of random forest or any decision forest into a manageable size and still have a very good predictive performance. Thank you for your time.
This was very interesting, and I have a question. When you're doing the pruning and you're only selecting the best trees, aren't you actually selecting those that happen to be great on the samples you have looked at, and you are actually working against the hypothesis that the trees are working together because each of them actually is misclassifying a different segment of the population. So when you only select the best 3 out of 50, for example, then yes, they were very great on this particular distribution. They might not be that great on another one because they actually have a bias of misclassifying certain segments of the population of instances which would not happen if you were keeping the full population of trees. So what is your intuition on that?
As you can see here in the merit formula, we have two parts. The numerator is is actually I'm measuring the correlation between the trees and the target attribute. But in the denominator, sorry, this one, I'm taking the correlation between the trees. So if they are accurate, but they are also diverse, I should prefer them on a different subset of the tree. Yeah, it's not only accuracy, because in the this is the part that you see here in the. No. Okay, the numerator is selecting the accurate, and the denominator selecting the diverse subset. This is why it can provide good results.
So since diversity is so important, then why limit yourself only to trees? So how can you compare forests to just ensembles of classifiers? Do you have any intuition on this?
You mean, again?
Instead of using 7 trees, use 7 different classifiers.
Yeah, of course. Actually, in my paper, I used also other kind of classifiers, not only decision trees.
And does it work better?
Yeah. It's also work in that case. But in decision tree, the full potential of ensemble learning can be shown. This is because of the disadvantage that we have in decision trees. When I try to look, ensemble learning can be done in every algorithms, but for instance, if we are trying to do it in SVM, the impact of ensemble learning is much lower. In decision tree, you actually can see it very dramatically. This is what I try to do here. The 3 drawbacks that you have in popular decision tree algorithms that you try to overcome using the ensemble learning. And this is very specifically for decision trees, and not for instance, in SVM or neural networks.
Yeah, in ensemble learning, not the trees necessarily, but people. We have been using a mixture of experts where you.
Yeah.
So does it not work with forests, or is it?
A mixture of experts sometimes provide better results, but usually you need another step to do the learning.
Another MLP on top of that.
Yeah. You can do that, but in decision tree usually it doesn't provide any extra improvement. In other kind of algorithms like Bayesian networks, it works better. In that case, the mixture of experts, and of course neural network, which is the origin of mixture of experts.